Today we are walking through the paper titled OpenClaw-RL Train Any Agent Simply by Talking.
Give me the big picture first. What is this paper really about?
At the highest level, the paper argues that every agent action creates a next state signal. The user reply, a tool result, a test audit, or a GUI change. Instead of throwing that away, OpenClaw-RL uses it as an online learning source so one policy can improve across personal conversations and general agent tasks in the same training loop.
What was missing in earlier work?
Earlier systems usually trained offline on fixed datasets. Even when feedback existed, much of it was reduced to a single good or bad reward, which throws away the specific correction hidden in the next state.
What exactly counts as the next state signal here?
It is whatever appears right after the action: a user response execution output, a test report, a GUI transition, or a tool return value. The paper's key point is that all of those signals can say both how well the action went and how it should change next time. Now let us look at the infrastructure overview.
Which design choice makes live training possible?
The design is fully asynchronous. Environment servers, the policy server, reward judging, and training run as separate loops, so the model can keep serving live requests while new interactions are scored and used for updates. That is what lets the same system cover personal devices on one side and cloud-hosted general agents on the other. The method overview shows the papers to learning paths binary ARL and hindsight guided on policy distillation, or OPD.
What does binary ARL contribute?
Binary ARL uses a process reward model, or PARM, to read the next state and assign a simple turn level score. That gives broad coverage because almost every scored turn can contribute, even when the feedback is short or only implicitly negative.
Then what extra signal does OPD recover?
OPD goes after the part that scalar rewards miss. It extracts a short hint from the next state, appends that hint to the prompt, and asks how the model's token probabilities would change under that corrected context. That produces directional token level supervision instead of a single yes or no reward. Here is the combined objective that ties the two signals together.
How should I read this objective?
Read it as the complementary pushes added together. The first term carries the broad reward signal from binary ARL. The second term measures how far the current policy is from the hint-informed teacher view, so it tells the model which tokens to push up or down. The paper introduces this because coverage and correction details solve different weaknesses.
And how does the framework extend beyond personal chat agents?
For terminal, GUI, software engineering, and tool call agents, the framework adds stepwise rewards on top of the usual outcome reward. The paper argues that long horizon tasks need credit assignment before the final answer. And this is where next state signals from tests, traces, and environment changes become especially useful. Now let us move to the personal agent results.
What changed in those personalization experiments?
The quantitative gap is large. The base score is 0.17. After 8 update steps, binary ARL and OPD each reach 0.25, while the combined method jumps to 0.76. After 16 steps, binary ARL is 0.23, so OPD becomes strong once enough hint-rich data arrives.
Does the paper show what that improvement looks like?
Yes. In the student setting, the agent learns after just 36 problem-solving interactions to stop sounding obviously AI written and to use a more natural casual style. In the teacher setting, after 24 grading interactions, it learns to write feedback that is both friendlier and more detailed. Finally, let us look at the general agent results.
What does the general agent result show?
The main point is breadth plus scaling. The same infrastructure trains terminal, GUI, software engineering, and tool call agents, using 128 parallel environments for terminal, 64 for GUI and software engineering, and 32 for tool call. The curves rise across all for panels, so this is not a one benchmark trick. The framework keeps improving across very different modalities and horizons.
Where do process rewards matter most?
Table 4 makes that comparison concrete. With integrated outcome and process rewards, tool call performance rises from 0.17 to 0.30. The absolute gain is much larger in tool call, which fits the paper's claim that stepwise feedback matters most when the task has longer credit chains.
So what is the main takeaway?
OpenClaw-RL treats next state feedback as a universal online learning source. Its asynchronous infrastructure keeps the system live. Binary ARL turns broad feedback into stable rewards. OPD turns corrections into token-level guidance. And the experiments show that the same recipe improves both personal agents and general-purpose agents.
So the paper's core claim is that next state feedback is not just a byproduct, it is the training signal.
Exactly. That is why the paper can connect live user feedback, environment traces, and long horizon agent training inside one loop without splitting them into separate problems. That wraps up this paper walkthrough.